All right, we're continuing our look at chapter 3 with additional derivative topics. Specifically in section 2, we're looking at derivatives of exponential and logarithmic functions. Okay, there are quite a few properties that are important with logarithmic functions that I would like to review briefly. We have talked about these a bit already back in chapter 1. So the log of 1 is always 0, so that's an important property to know. This would work with ln also, so like the natural log of 1 is also 0, so it doesn't matter what base you're working with. Here, as long as these two bases match up, then whatever the exponent is of that b, that's going to be your answer. So this would be b to the first. So that means that would be just 1. Here, these match up, and so they match up. That means all that cancels, and you're just left with the x. Same thing here. As long as these match, then all that cancels out, and you're just left with the x. We've got these other properties here where you're splitting apart. When you have logarithms of two quantities that are multiplied together, you can split it apart into the log of each one at the two logarithms added together. Here, if you have the log of two quantities that are divided, you can split that apart into the log of these two separately being subtracted. This one, if you have the p in front, you can bring that down as a coefficient. So sometimes that makes it easier to work with and solve. And then the last property is if the bases are the same and you're taking the same logs, then that means these two things have to be the same as well. Okay, so applying some of these, we want to be able to solve these without using a calculator. So on one like this, what I would suggest doing is trying to rewrite 81 as 3 to some power. And if you do the prime factorization of 81, we know that 9 and 9 go into it, and then 3 goes into 9. So we'd have 3 to the 4th is going to be equal to 81 doing the factor tree. So this will be the log base 3 of 3 to the 4th. And that lets us use our property that says if this base and this base match, then all that cancels each other out and we're just left with our exponent, which is the 4. Okay, this one basically could be done the same way. We want to see, could we rewrite 64 as 4 to some power? So 4 squared is 16, and it turns out 4 to the third is 64. And we get these two bases that match, and we're left with just 3 as our answer. Okay, sometimes it's just helpful, depending on where the variable is, to put it in exponential form. And again, going back to chapter 1, exponential form means you start here, you raise it to this power, and then you set it equal to the x. So that's going to be 5 to the negative 1 is equal to x. This would be 1 over 5. So x would be equal to 1/5. This one, if I put it in exponential form, I'm going to have 10 to the negative 3 is equal to x. So 1 over 10 to the third is equal to x. Okay, this one, if I rewrite this, we know that when we have natural log and e side by side, they'll cancel each other out. But they won't cancel each other out if they have something in between them like this. We need to get rid of that radical. We're going to do that by writing it as e to the 1/3 power. You remember we said you do the power over the index, so 1 over 3. Now, because they are side by side, they do cancel, and we're left with the 1/3. And then the last one, if we want to put this in exponential form, generally, if you've got log like this, a lot of times we're going to put it in exponential form. So the base for natural log is e. So I'm going to do e raised to the second power is equal to x. So e to the second is equal to x. So that is what x is equal to. It's equal to e to the second. And so that's my answer. Here we're going to use the logarithmic properties to write these in simpler terms. So basically, splitting it up, splitting it up, bringing exponents down as coefficients, things of that nature. So like this one, we're going to use the sixth property, and because we have two things being divided, so that property is going to let us split the division up into two separate logarithms that are being subtracted. So that would be writing it in simpler terms. Here, the natural log and e are paired side by side with nothing in between, so those cancel and just give us the x. That would be using property number 3. Okay, this one I'm going to use property number 7, and that one says if I have an exponent here, I can bring that down as a coefficient in front. So that's going to be 5 natural log of x. Okay, this one I'm going to use the fifth property since I've got two things multiplied together. So I'm going to split the multiplication up into addition of two separate logarithms. So I have the natural log of x plus the natural log of y. This one's got a lot of things going on. It's got some multiplication, it's got some division. So I'm actually going to be using numbers 5, 6, and 7 to do this. So if I split this one up, I'm going to do the division, separate that part first. Okay, so I'm going to subtract the part that's divided is the part that gets subtracted. So I've got the natural log of the numerator minus the natural log of the denominator. Okay, when I break this apart, because I do still have things multiplied together here, I'm going to break it apart as the natural log of u plus the natural log of v squared minus the natural log of w. So looking at this, since these are multiplied, that's why this breaks into two things added together. And then this is almost there. The only thing we need to do is bring this 2 down in front. So I'm going to have the natural log of 2 plus 2 natural log of v minus the natural log of w. All right, the last one here, again, has several things combined together. So I'm going to break it apart. I'm going to do the division part. So I'll have the natural log of u squared minus the natural log of v to the third w. Okay, so on this one, I'll bring the 2 down in front. Because I'm going to be breaking this apart, I'm going to put this all in parentheses. So I'll have the natural log of v to the third, and since these are multiplied together, I'm going to add those. And then the last step is I need to bring this 3 down in front. So I'm going to have 3 natural log of v plus the natural log of w. If you wanted to distribute the negative through, you could have 2 natural log of u minus 3 natural log of v minus the natural log of w. Okay, all this reviewing of exponential and logarithmic functions is really to get us to the point of taking the derivative of these exponential and logarithmic functions. So the derivative of the exponential function e to the x is e to the x. So it is its own derivative. So it's a very special function in that characteristic. Okay. So the derivative of e to the x is e to the x. Okay. So you do need to make sure that you use the designated e key on your calculator when you are using that. So because that's the one that has the correct value stored in there. And that's the one that's going to be just above the ln key. Okay, so just like a word of caution here, the power rule that we've used before where we bring the exponent down in front and decrease the power does not work for these because what happens is this is a constant and then the variables in the exponent. So for the power rule to work, it needs to be a variable raised to a constant. Okay, so just a quick review of the logarithmic function and the properties of the natural log. We've got, if we have the natural log of b to the x, then b does need to be, our base does need to be greater than 0. Can't be equal to 1 either. And when you put that in the exponential form, it's going to be b raised to the y is equal to the x. So that's where you get that. So the domain of the logarithmic function is 0 to infinity. So we can't take the log of any negative numbers. And the range is all real numbers. And then the reverse of that is true for exponential functions. For exponential functions, the domain is all real numbers and the range is positive numbers, 0 to infinity. Okay, and these two are reflections in the line y equals x. So this is that diagonal line y equals x. So the exponential function and the logarithmic function with the same base are going to be reflections in the line y equals x. And the two most commonly used logarithms are those that have a base of 10, which we call the common logarithm, and those that have a base of e, which are the natural logarithm. Okay, so another derivative rule here, if we're looking at the natural log of x, the derivative of that is simply 1 over x. So again, that's a fairly simple rule to use. Just keep in mind that x does need to be greater than 0. Okay, so applying these rules here, if we look at this, we want to find the derivative here. So the derivative of this is, we've got this constant that's out in front, so we're going to do 3 times the derivative of e to the x. Well, the derivative of e to the x, we said, is itself, so it's e to the x. Here we've got a constant multiple, so we're going to have 5 times the derivative of natural log of x is going to be 1 over x. There's not a lot of simplifying we can do here. The most we could do is write it like, okay, next one here, if we do the derivative, this actually does use the power rule, okay, because we've been taking derivatives of things like x to the 4th. So we'll bring the 4 down. We're going to reduce the power by 1. And so the derivative of x to the 4th is 4x to the 3rd. Now, looking at this part here, I actually want you to think of it like we looked at those properties. So we want to bring that 4 down in front. Okay, so now when we bring the 4 down in front, we have the constant times the ln of x. Here, we haven't learned how to do the natural log of x to the 4th, but we do know how to do the natural log of just x. That's why we want to bring that 4 down in front so that we can apply that rule that we've learned, okay? So our derivative here is going to be 4, and the derivative of natural log of x is 1 over x. So we'll have 4x to the 3rd minus 4 over x. Okay, a couple for you to practice with. This is really concentrate on which property you are applying when you take the derivative of each term. Okay, so for A, you've got the constant multiple times the derivative of e to the x, which is e to the x. Here we've got the constant multiple times the derivative of x squared. Well, the derivative of x squared is 2x to the 1st. Here we've got 7 times the derivative of x. Well, the derivative of x is just 1. And then the derivative of a constant is 0. So we have 4e to the x plus 8 times 2 is 16x plus 7. All right, the next one here, if we take the derivative, this is the power rule, so this is going to be 7x to the 6th. Another power rule, so 5x to the 4th. This one we've got to be careful about because e is a constant and 3 is a constant. So all of this is just a constant. And we saw up here that the derivative of a constant is 0. Here, the derivative of x is just going to be 1. And then the derivative of e to the x is e to the x. So we have 7x to the 6 minus 5x to the 4th minus 1, and then plus e to the x. So that one's really testing your understanding of differentiating each type of term there. Okay, a couple more to practice with. The derivative here, 10 is a constant, and then the derivative of x to the third is going to be 3x squared. The 100 is a constant, and the derivative of natural log of x would be 1 over x. So I'm going to have 30x squared minus 100 over x. All right, this one, we need to do a little bit of simplifying before we start taking derivatives. So the first thing I want to do is I want to move this down in front. Keep in mind that's not taking a derivative. That is a property of logarithms that allows us to do that. So I'll bring the 5 down in front. E to the x I'm going to leave like it is. And then this, if you recognize the natural log and e are pairing together and canceling each other out. So we just have 2. So all we did is simplify and rewrite to get this. We have not taken a derivative. So now if we want to take a derivative, we'll have 5. The derivative of natural log of x is 1 over x. The derivative of e to the x is e to the x, and then the derivative of 2 is 0. So we'll have 5 over x plus e to the x. Okay, in most applications that involve logarithmic and exponential functions, we do prefer to work with e as our preferred base. Okay, so we've looked at taking the derivative of e to the x, and that one simplifies very easily to just be e to the x. But there are going to be times you might have something like 2 to the x or 5 to the x, and you still need to take a derivative. So we do have another rule that applies in those cases. So if I'm taking the derivative of b to the x, with b being basically anything but e, looking at that, our rule says it's going to be the same thing times the natural log of whatever that base was. Okay, so that's our rule there. And if we're looking at the derivative of the natural log, well, again, we prefer to work with natural log, but that's not going to happen all the time. So if we have just a log with a different base, then our rule with that is 1 over the natural log of the base times 1 over x. So this part was already the 1 over x. This is just the part that compensates for the fact that we're working with a base of b and not a base of e. Okay, so applying these derivative rules that we just looked at, okay, for this one, we've got the log of 5, log with a base of 5 of x. So just to kind of show you what I'm using, I'm going to be using this rule here. So that tells me that I'm going to have 1 over the natural log of my base times 1 over x. Okay. So 1 over the natural log of my base, which is 5, and then I'm going to do 1 over x. There's really not a lot I can simplify. I could write it potentially like this. There's not a huge gain in doing that. Okay, so, and this was the rule that we were using. This one, we've got a couple, we want to take the derivative of 2 exponential functions that are being subtracted. So the derivative of each one of those is going to be an application of this rule here, because we have a base of 2 and then a base of 3. So my base of 2, if I look at this, it's going to be 2 to the x times the natural log of 2, and then I'm going to subtract from that 3 to the x times the natural log of. All right, a couple for you to practice with. If I take the derivative of this first one here, this is just a power rule, so I'm going to bring the 10 down and decrease it by 1. But this uses the derivative of an exponential function. So what that tells me is that I'm going to do the 10 to the x times the natural log of that base. So times the natural log of 10. Okay, this one, we're going to be using our derivative rules for logarithms. So here we're going to have 1 over the natural log of 2, because it's 1 over the natural log of the base, times 1 over x. This is just a constant multiple. And then I'm going to apply it a second time here. So it'll be 1 over the natural log of 5 times 1 over x. So I'll have 1 over x times the natural log of 2 minus 6 over x times the natural log of 5. Okay, so an application problem here of what we've been looking at. So we've got an online store that sells guitar strings. If the store sells X sets of guitar strings at a price of P dollars per set, then the price demand equation is given to us here. We've worked with price demand equations before, so we want to find the rate of change of the price, okay? So anytime you see the word rate of change, that's telling me that I need to take the derivative. Okay, so I need the derivative of the price. Okay, so we want to find the rate of change of price with respect to demand. So demand is our X. When the demand is 100 sets of guitar strings, and interpret the results. Okay, so I'm going to find the derivative of this function here. Okay, so I have a constant multiple. That's the 12.5. And then our rule says we're going to have our exponential function, and then we're going to have the natural log of our base. Okay, and so that's going to give me the derivative of the price function, which is what I'm asked to find here, except I need it evaluated at 100. So I'm going to find the derivative at 100. And so that's going to give me negative 0.0205. So when we're looking at the rate of change of the price, we're actually, because it's a negative, we're going to have a decrease. So it's going to be decreasing by about 2.05%. And I said percent. I should have said cent. Okay, so the price per set of strings is decreasing. Again, decreasing because of the negative. And it is talking about money, so it should be cents and not percent. But about 2 cents per set when the demand is 100 sets of strings. So always remember to include what level of demand you're talking about. All right, so we've got one for you to practice, very similar to the one that we just got through doing. An internet store sells reversible fleece blankets. If the price demand equation for the blankets is given to us here, find the rate of change of price. So in other words, find the derivative of price with respect to demand when the demand is 400 blankets and interpret the result. So we want to first of all find the derivative. Okay, so that's going to be that constant of 200 times the exponential function itself, and then times the natural log of the base of that exponential function. Okay, so we want to evaluate that at 400. So 200 times 0.998 to the 400th power times the natural log of 0.998. Okay, so it's decreasing because of the negative, and it's decreasing at a little at about 18 cents per blanket. Okay, we want to look at this example. A model for the growth of a sandwich shop franchise is given here, where N of T is the number of locations in year T, and that corresponds to 1980. So we're going to be asked to estimate the number of locations in 2028 and interpret the results. So if we do that, if we're estimating the number of locations in 2028, Well, t equals 0 corresponds to 1980. So 2028, if we check and see how many, if we subtract those, we're going to see that 48 years have elapsed. So we're actually going to plug 48 into this. So we'll have negative 765 plus 482 times the natural log of 48. So we're going to have approximately 1,101 locations after 48 years if it follows this model here. Okay, so we estimated the number of locations and we interpreted the results. So that's going to be the number of locations we would expect to have after 48 years. Okay, so the next question is to estimate the rate of change in the number of locations. So in other words, the derivative. Okay, so we want to find the derivative of this expression. So that's going to be n prime of t is equal to, the derivative of a constant is 0, so I don't need to include that. This is going to be a constant multiple, so 482 times 1 over t, so 482 over t. And we want to evaluate that when, again, t is 48, because that's how many years we'll have elapsed. So we're going to get approximately 10 locations. So what that's telling us is in the year 2028, the number of locations is growing at a rate of about 10 locations per year. 10 new locations per year is what that value is telling us. Okay, here's one you can practice. A model for a newspaper circulation is given where C of t is the circulation, and this is in thousands in year t where t equals 0 is 1980. Use the model to estimate the circulation and the rate of change of circulation in 2026. Round both to the nearest hundred and interpret these results. Okay, so the circulation itself is just going to be, if we look at, if t equals 0 is 1980, then the difference between 1980 and 2026 is going to be 46 years. Just subtract those. So we need to figure out the circulation after 46 years. So that'll be 83 minus 9 times the natural log of 46. So 48.5. So basically that's in thousands. So 48,500 is going to be the newspaper circulation. Okay, we also need to look at the rate of change of circulation. So we're going to take the derivative. So here's our equation. We're going to take the derivative of, so the derivative of 83 is a constant, that's 0. So we're going to have minus 9, so that's the constant multiple, times the natural log of t, so that's 1 over t, so negative 9 over t. We need to evaluate that in the year 2026, which is when t is 46. Okay, so we get negative 0.195 or approximately negative 0.2. So in that year of 2026, the newspaper circulation is projected to decrease because we have a negative here. It's projected to decrease about 200 papers per year. Because remember, this is thousands. So if I have 0.2 thousand, then 0.2 thousand is actually the same thing as 200 papers per year. Okay, last example here. We continue to talk about tangent lines and equations of tangent lines. So this is one that it uses e to the x. So our plan here is in writing the equation of the tangent line, we need to have both a point and we need to have a slope to work with. Okay, so the point is going to come from the original function and the slope is going to come from the derivative. So I want to use x equals 0. So if I evaluate the original function at 0, okay, anything to the 0 is just 1. So 3 times 1 is 3. So that means f of 0 is 3, or I have the point 0, 3. As far as the slope I use the derivative. So the derivative of 3e to the x is actually 3 times the derivative of e to the x, which is e to the x. So it is the same thing. It should just be an x. Okay. So I need to evaluate that at 0. So that would be 3e to the 0 again, which is just 3. So my slope would be 3. So I'm going to do y equals mx plus b using this point and this slope. So 3 would be equal to 3 times 0 plus b. This will be 0, so b is going to be equal to 3. So I'm going to have y equals 3x plus 3. Substitute in the m and the b for your equation.